So now that we've looked at being able to solve these applications with the damping constant, now what we're going to do is we're going to go ahead and take a look at these sorts of differentials, second orders, that have not only just the damping constant, but also some sort of forced motion acting upon the system. And so essentially when you have a forced sort of motion, what you're going to have is you're going to have two different components that affect the solution or the motion of the solution. And the first one is going to be the idea that there's going to be some initial force from the damping as well as the effect due to gravity, etc. And that's what we call the transient solution. The transient solution is going to be basically the complementary solution component, and that has sort of a temporary effect. But eventually, as time goes on, the transient solution or the effect of the transient solution is going to be essentially not going to be anything that influences it. The steady state solution, or more particularly the particular solution, is going to kind of model what the long-term behavior is. So there's going to be a narrow window in the beginning where the transient solution has a pretty decent effect on the overall equation of motion. But after time passes, that transient solution is going to be negligible and the steady state solution is going to overtake the behavior, it's going to dominate. And so think about this. There's an idea in some sort of motion to where, let's say you have a wind chime and it's attached to some sort of string, and the string basically, like if you were to drop it, has like an initial sort of refraction to it, and so it's going to bounce maybe once or twice, but eventually the wind is going to have more of an effect than anything. Okay, so it's an initial drop. And same thing with, like, if you're on a ski lift, maybe if you initially jump onto the ski lift, you might bounce the ski lift up and down a little bit, but eventually the bull wheel is going to basically be the model of that equation of motion, and it's going to say what's going to happen after a little bit of time. And so I have a model below that shows the solution, and it shows both the transient solution, the steady state solution, and also the equation of motion, which is the solution in general. And so if you look in blue is going to be the steady state solution. In black is going to be the equation of motion. And notice initially the equation of motion is more governed by the transient solution. But over time, it looks like that the black and the blue, in other words, the steady state and the equation of motion, are essentially going to converge to one another. And that's generally true of what happens with these sorts of systems, is that the transient sort of solution in the short term is dominant. Okay, in the long term though, the steady state solution is going to be what governs the real motion equation. So let's take a look at an example of one of these types of systems and see if we can model it. So we have a 16-pound weight, stretches a spring 8/3 of a foot, and the weight initially begins 2 feet below the equilibrium point. And subsequent motion takes place in a system that offers damping 4 times the instantaneous velocity. The weight's driven by an external force equal to F at t equals 10 cos 2t, and it's released with an upward velocity of 1 foot per second. So we're going to go ahead, find the equation of motion, identify the transient and steady state solutions, and then graph everything and kind of explain what's going on with that. All right, so first things first, let's model what we have. We know right away that from previous problems we have F equals ma. 16 is the force, mass times 32, which is acceleration due to gravity, or 1/2 of a slug is the mass. We know beta is 4 because it says right here that 4 times the instantaneous velocity. F is equal to kx, or in other words, k in this case is going to, is 16. K is unknown. X is the distance stretched beyond equilibrium, which is 8/3, and then 3 times 6 is 48. 48 eighths are 6. All right. And then finally, the easiest of these to identify is the function, the forced motion, and that's going to be 10 cos of 2t. Right. So now we're just going to throw everything together. We're going to get a equation of motion, and let's start with the complementary. Okay, so what we're eventually going to have is we're eventually going to have this x double prime plus beta, which is 4 over m, which is 1/2 x prime, that governs the velocity, plus the spring constant 6 divided by 1/2 x, which is going to be equal to the 10 cos of 2 t. And this is what's going to give us a little bit of trouble. All right, we haven't seen an equation like this because everything else is going to be everything else thus far has been the type where we have a homogeneous. Right? Simplifying, x double prime plus 8x prime plus 12x equals 10 cos of 2t. And finally, let's just go ahead and get the complementary solution, which is defined as m squared plus 8m plus 12 equals 0, factoring m plus 6, m plus 2 equals 0. So we get a case 1 where we have -6 and -2 as our two solutions. And so we get yc is equal to c1 e to the minus 6t plus c2 e to the minus 2t. And we're going to hold on to that because we still need to figure out what the particular solution is for this. And as you know, particular solution's not a lot of fun to try to compute, so let's go through that. So for yp, we need a guess. And our guess that we can start with is that y is going to be equal to a times cos 2t, but also plus b sine of 2t. All right, so we have to be careful because remember, successive derivatives of sine can eventually lead to a factor of cosine as well. Y prime is going to be equal to -2a sine 2t plus 2b cos 2t. And then finally, the second derivative is going to be -4a cos 2t minus 4b sine 2t. All right, and as you can imagine, it's not going to be a lot of fun being able to find our particular solution because now we're going to have to stuff all of those back in to this. And I probably should have named them x instead of y's because we're not dealing with anything with a y in here. So let me just, for nomenclature's sake, just name everything x instead. It's a small error, but nonetheless, let's just make sure we're consistent. All right, so now we're going to substitute. All right, so we have x double prime. So we're going to have -4a cos 2t minus 4b sine 2t plus, now remember we had 8x prime. All right, so we have this 8x prime. So 8 times -2a sine 2t plus 2b cos 2t. And then I think we had 12 for x. Let me just verify that. Yep. So 12 times our a cos 2t plus b sine 2t. And all of that, remember way back, was equal to 10 cos 2t. All right, so now we can start to combine some like terms. All right, so notice that we have a -4a cos, and down here we have 12a cos. So that's going to turn into 8a cos 2t. We have -4b sine 2t, and then we have 12b sine 2t. So that's going to be a positive 8b sine 2t. And unfortunately, the rest of it is not going to be like terms, so we just distribute the 8, and we're going to get plus a -16 times a sine 2t plus 16b cos 2t. And that's going to be equal to 10 cos 2t plus 0 sines of 2t. All right, remember we need the 0 in there just to build the system. All right, now, as bad as that is, it does get a little bit better. All right, so we're just looking at the coefficients. Okay, so we have an 8a cos and we have a 16b cos. So one equation we can get from the system is that 8a plus 16b, which are the coefficients of cosine, are going to be equal to 10, which is the coefficient of cosine on the right-hand side. All right, so that's going away. And now we have negative 16a, and then we have positive 16b, is going to be equal to, excuse me, let me get rid of that. It's not true. So we're just looking at coefficients of sine. So that's negative 16a, and then also 8b. And that's going to be equal to 0. All right, and you can start to see that this is actually going to be a really nice system. All right, let's just multiply the first equation by, we can multiply it by 2. So if we multiply that by 2, we get 16a plus 32b equals 20 minus 16a. So this one's by 2, and we just multiply that by 1. We didn't do anything. Plus 8b is equal to 0, and that's a negative. Those a's go away, and we're left with 40b is equal to 20, or after all of that, b is a half. That's really nice. And then also, we're going to substitute 1/2 back in for b. Let's just substitute it right here to make it really nice and easy. Minus 16a plus 8 times a half is going to be equal to 0. And then we can just see the writing on the wall for this, that a is going to be equal to 1/4 for us. All right, so obviously this is 4. Negative 4 divided by negative 16 is 1/4. So our particular solution, yp, is going to be equal to, now remember, a was the coefficient of the cosine, so 1/4 a cos 2t, plus 1/2, which is b, which is the coefficient of the sine of 2t. And mercifully, we can get our, and it should be xp, excuse me, and finally we can get x at t is going to be equal to, so remember we had c1 e to the minus 6t, all right, and this is all the way back up for the complementary solution. So xc plus c2 e to the minus 2t, and then we have this 1/4 cos 2t plus 1/2 sine 2t. And we're going to hold on to that. We're going to go to another video because we do need a little bit more time. But just make sure that all of this makes sense for at least the solution. Then we can find the particular solution for this, talk about the transient, talk about the steady state solution, and then finally graph all of these. All right, so I'm going to finish this up in another video.